Let me first introduce the speaker. So today's speaker is Anna Gilbert, and she received her Bachelor of Science degree from University of Chicago, and the PhD in mathematics from Princeton University in 1997. And she was she was in AT&T Bell Lab and until 2004. And then from 2004 to 2020, she was in the Department of Mathematics in University of Michigan, and also has a secondary appointment in the EECS. And she eventually became a Hermann Goldstein professor. And in 2020, last year, she moved to Yale and became John Malone Professor of Mathematics. And she's also a professor of statistics and data science. Her research interest is in analysis, probability, and algorithm. And in algorithm, she's particularly interested with algorithm with application to harmonic analysis, signal and image processing, and machine learning. She received many prizes, and but I will only just mention two of them. One is the National Academy of Sciences Award for Initiative in Research in 2008, and the Siam Ralph Kleinman Prize in 2013. So let's start today's colloquium. Thank you.
Okay, great. Thank you. It is a real pleasure to be here virtually. Fortunately, I have visited Harvard a number of times. Most recently, a CMSA workshop on big data in August of 2019, and so it's a pleasure to be here again virtually. So I'm going to talk about work that covers, roughly 3 to 4 years of the past 3 to 4 years of work in sort of a new area for me. And it covers work with a number of different people listed here in a variety of papers and configurations. Rishi is my current student, and he will be graduating in a few weeks. Lalit Jain was my postdoc for a year and has since moved on to the business school at the University of Washington. And Ben and Greg, I have actually never met in person, but we have succeeded in writing now 2 or 3 papers together. Even pre-pandemic, we were collaborating virtually. So it's a great collaboration, and I hope to meet them in person someday. Okay, so I'm gonna give you a very high-level overview of sort of this area of work, and then we'll dive into the various pieces. And we're gonna start with the idea that if you have distances or geometric descriptions of your data or of your data points, and somehow these distances have been corrupted or distorted in some way, then you're going to end up with a distorted view of reality. And in fact, actually, reality might be quite different from the view that you have. At sort of a higher level, or I guess I should say maybe at a lower level, mathematical question is sort of what happens in all of these, in many machine learning algorithms. What happens if you don't get the geometry of the data correct? What happens if your image is just your view of the data is distorted? How badly does that affect downstream algorithms? Said another way, many machine learning algorithms presume that the input is correct, or maybe they allow for some noise, but not really. And so I'd kind of like to know how badly can things fail, and can we improve them? So to give you an idea of how badly things can fail, we cooked up this example, which should show you the failure of one of the standard manifold or embedding dimension reduction algorithms. It's called isomap. And I'm going to walk you through slowly how we cooked up this example, because it's actually kind of disturbing how little things have been perturbed and yet how badly the outcome is. So we take the Swiss roll data set, which is it's a canonical data set for manifold embedding, and we've got 2,000 data points in here. They're colored so you can sort of see where they should lie. And this is the original data set. In order to generate these two pictures, we did the following things. So first of all, we computed the pairwise distance matrix for all of these 2,000 data points, so 2,000 by 2,000, symmetric with a 0 along the diagonal. And we added just a little bit of Gaussian noise to 5% of the entries in this matrix. Then we used these distances, again, slightly noisy, to infer a graph, the 30 nearest neighbor graph G from these distances. And then we did the following thing. We said, look, you've got a graph from the perfect data set, and then you've got a graph from the ever so slightly corrupted distances. The graph from the ever so slightly corrupted distances has the same edges as the clean graph. It's just that the edge weights have been perturbed by only 8.5%. Okay, so the same vertices, the same edges, just slightly different edge weights. And if you use both graphs as input to the same algorithm, which is called isomap, and you then run isomap on these two ever so slightly different inputs, you get two wildly different looking outputs. So, in the first one, it's this clean data set. Everything's been projected onto this beautiful spiral, and you can see where all of the data points are supposed to lie and how they're related to one another. You're Melanie, right?
Yes. Yeah. Sorry, I had a question. What are the edge weights supposed to be? Are those supposed to be the distances, or?
Yes.
Okay.
Yes. Okay, cool. So I hope you are convinced, ever so slightly different graphs and two incredibly different outputs. And the theory result for isomap is that it's reasonably, it's somewhat robust to little perturbations in the data points themselves. But that says nothing about the distances being corrupted between or amongst the data points. This would lead me to believe that these machine learning algorithms are actually quite sensitive to distorted distances. And if you've got a corrupted view of the underlying space, you're not going to get a very good picture. So I was thinking about this because I had spent a year or two listening to lots of computational biology talks in single cell sequencing data, where you have very large matrices that are some number of cells by 20,000 genes, and each entry is the frequency count of expression of a gene in any single cell. And these data are just incredibly sparse. 90% of this giant matrix will be 0. And so when you try and figure out, where do these cells lie with respect to one another? How should I cluster them? What type of cells are what? Can I characterize, cancer stem cells by the expression of certain kinds of genes? When you want to try and get a picture, so to speak, of cells based on their gene expression, any kind of distance that you compute between the cells to get an idea of, what cell is close to what other cell, you're just going to have garbage. The entries are corrupted, and these values are incredibly low. They're just wrong because you've got sparse data. And people will do all kinds of things to normalize these rows, to clean up this data, but it's not really clear what works the best or why. And it's also not clear what the performance of many of the downstream machine learning algorithms that people are trying to use. It's really not clear what effect any of these, ad hoc methods, have to do. So I thought, we should try and address these questions in a more principled way. And the metric that you use or that one derives, that captures the geometry of the data, it should get somehow the salient features of the data. And we should trade off, sort of the geometry in which we express the data points and the features that sort of distinguish them. And we should strive for a good representation of the data that might give us insight into how it's generated. One would hope that compact representations, like reducing the dimension, or a simple example like projecting onto the first couple of singular values or principal components, you would hope that compact representation gives you insight and speeds up some algorithm that you're going to use. So these are the kinds of questions that we're striving for, and to do so with good underlying geometries. Okay, so we are rapidly coming to precise problem formulations, so you can understand, oh, that's what she's talking about. So I'm going to talk about two types of problems. The first one of which is a convex optimization, sort of as a general framework, and it's convex optimization with metric constraints. So I want to optimize such and such kind of function subject to all the variables must satisfy, the properties of a metric. And then the second problem I'm going to talk about, it looks at the outset like a sparse signal recovery or compressed sensing problem or a sparse approximation problem, but one should not be fooled by that. Despite 15 years of beautiful work in that, that's actually the wrong approach. And the right approach is to think more combinatorially. So I'm going to talk about that. And recurring in each story is the all pairs shortest path problem. So yes, recurring in each story is essentially an algorithm that you can teach undergraduates. Okay, so that brings me to the first problem, metric constrained optimization. Okay, so to set the stage for these problems, here are some definitions of the characters we're going to work with. We have a distance function, little d. It maps from our data set to the real line. Capital D here is going to be a matrix of pairwise distances. And I sometimes think about the data set X, or I think about the graph G that's induced by the data set, the vertices being the data points, the edges being which data point is connected to which other one, by what kind of distance or similarity measure. W here is some kind of weight. I like to think about this graph G sort of in a nice general form, because I would like sometimes to look at problems where this data point is not at all related to this data point. It's quite dissimilar. And so maybe if I build a graph, I don't want to put an edge between these two. In the most straightforward case, my graph is simply the complete graph, and the edge weights then are just all the distances amongst the pairs. Okay, so I'm also going to be interested in optimizing over met n, the metric polytope on n points. And I also, when I look specifically at graphs that aren't the complete graph, I'm going to be interested in the metric polytope that's the projection of the metric polytope onto the coordinates given by the edges of the graph G. In other words, we're going to look at distances that are only between pairs of points or vertices that are adjacent in G. Okay, and then the thing to observe is that a point is in the metric polytope of G if and only if we have no cycle constraints that have been violated, which is the generalization of the triangle inequality, a triangle being a cycle of length 3. So in other words, if for every cycle in G and all of the edges in the cycle, now I can make this colored, the edge weight between this edge weight should be less than or equal to the sum of the edge weights, in the rest of the cycle, which is exactly the generalization of the triangle inequality. Okay, so this is what it means for a point to be in the metric polytope of G. And you should observe that this is the intersection of possibly exponentially many half spaces. Okay, so I am teaching algorithms and optimization this semester to the statistics students. And I have to give some lectures on linear programming. And so I feel like these kinds of settings occupy a lot of my brain space in the last couple of weeks. Okay, so these are the players. Okay, so I claim that we're going to be able to tackle a whole bunch of different problems that have to do with sort of organization of data and machine learning, and they're all of the form, optimize some objective function subject to a bunch of constraints that look like, such and such must be a metric. So let me give you some examples. Let me give you the first example, which I think is the clearest, although it's not the most interesting. So suppose you're given a matrix D. It is ostensibly an n by n matrix of distances amongst points. Now, it might have been corrupted, there might be noise, it might not actually be symmetric, some of it might be garbagey, and various triples in this matrix may not satisfy the triangle inequality. So I would like to find the closest metric or the closest matrix in the metric polytope to the input matrix. Now here, I mean closest in some LP norm. And here I really mean norm. I want you to remember that, P between 1 and infinity inclusive, because in the second half of the talk, I'm going to change that. Okay, so the closest point in the metric polytope to the given matrix, i.e. repair this garbagey matrix of distances, by giving me a cleaned up matrix that satisfies all the triangle inequalities and is a proper metric. Okay, so that's sort of the first obvious example. Hopefully you all see, yes, that is an objective function, and this is a bunch of constraints, a bunch of inequality constraints. Okay, so there are other problems that that are similar to this. Okay, the first one of sort of practical interest is what's known as correlation clustering or weighted correlation clustering. And this is the idea that you're given a graph and you're told, you're given similarity or dissimilarity measures on each edge in the graph, saying, these two vertices are similar and these two vertices are dissimilar. You'd like to partition the nodes into two clusters so as to put those that are dissimilar in the two different clusters and those that are similar in the same clusters together as much as possible. Okay, now as much as possible means construct a reasonable objective function. This is a reasonable objective function. I'd like to minimize, those things that are similar go together and those things that are dissimilar are not together. But the only problem is this is not a convex problem, and it's not particularly amenable to reasonable algorithms. So what people typically do is relax these constraints. These are integer constraints. X is either 0 or 1. They relax them to X is in between 0 and 1. It's just that these distances here, these partitions must satisfy a triangle inequality. So now here I want to minimize some objective function subject to all the variables must satisfy a triangle inequality in triples, and they must be between 0 and 1. Okay, metric constraints and some objective function. Okay, here's another version. This is general metric learning, and I want to emphasize that this is very general metric learning as opposed to the original formulation, which was essentially find a reweighting of Euclidean space, which I didn't find very satisfying. Okay, so here is the general form of the problem. You're given a data set and you're told this collection of pairs are similar and this collection of pairs are dissimilar. We'd like to learn a metric on the data set so that the distances between pairs that are similar are small, and the distances between pairs that are dissimilar are large. And so you can, as much as possible, we can formulate as the following objective function. I'd like to minimize, put things that are similar together, put things that are dissimilar far apart. And I would like this matrix M that is giving me distances between X and X prime. It should satisfy a metric, i.e. it should be a point in the metric polytope. Okay, so here is an objective function subject to metric constraints. Okay, hopefully I have convinced you that there is a fairly rich class of problems that you might think of as metric constrained problems, where you're given, to be pedantic, a nice strictly convex function f, some graph G, a finite family of half spaces that are going to be our linear inequality constraints. And we want a unique point that is in the intersection of all of these constraints that minimizes this objective function. Okay, now I've added in these extra constraints, this finite family of half spaces in here, because like for the weighted correlation clustering problem, we might want to add, not only are the entries in X, not only do they satisfy all these triangle inequalities and whatnot, but also the entries are between 0 and 1. So, I want to add in some generality to allow for that. Okay, so if you look at this problem, you say it's a beautiful convex optimization problem, right? I've got a lovely convex objective function. I've got lovely constraints. What could possibly be wrong with this? Why can't you just go solve this? Well, unfortunately, the existing methods don't work. I mean, they don't work in the sense that these are just way too many constraints for existing algorithms to be at all feasible. So, there are many constraints. If all you're doing is a simple triangle inequality constraints, you've got n cubed of them. That's a lot. And if you're talking about cycle constraints for a graph, you might have exponentially many. That's just too much. So the existing algorithms simply don't scale to do these kinds of problems. There are too many constraints. If you try some of the modern tricks, you try and sample the constraints, then, imagine you're trying to sample an exponential sized set. You're going to be sampling for quite a while in order to see every single one of those constraints enough times. So that translates to too many iterations. If you try and come up with some Lagrangian formulation, you again have too many iterations. So existing optimization techniques just simply do not work. So Rishi and I, Rishi's my student, we encountered these kinds of problems in trying to solve something else. And Rishi said, maybe we can subtly adjust some of the previous sort of active set methods or that use Bregman projections, maybe we can very subtly adjust them with the right kind of separation oracle. And so he came up with an iterative algorithm for solving these kinds of problems. And it is in the following 2 stages. So in the first, so I guess I should say, before you do these 2 stages, you have a list of active constraints. And it's a Bregman projection type algorithm that doesn't need to look at these constraints cyclically. So it's not sort of going to cycle through all of them. It's not going to sample them. It's going to maintain an active set of reasonably good ones. Okay, and it's going to do a Bregman projection onto them. And then it's going to say, you know, if I didn't do any Bregman projection and I haven't updated the variables that correspond to, you know, this particular inequality, then I can just throw it out. I don't need to remember those constraints. I can forget them. And we analyzed the algorithm with appropriate hypotheses. It converges to the global optimal solution. And with even further appropriate assumptions on the Hessian of the objective function, the optimality error decays exponentially fast. And what's kind of neat is when the algorithm terminates, the set of constraints are exactly the active ones. And you know, we also developed a stochastic version. Those of you who A, are following carefully, and B, really following carefully might be saying, how do you get this? You know, it seems like you're getting something for nothing. In particular, how do you make this list of constraints when there are possibly exponentially many of them? How do you do that with any kind of efficiency? And I'm going to say that's where the magic comes in. That is in this very first step of the general algorithm. I want to emphasize there are 3 phases to this algorithm. While we're not done, do the following. Query an oracle and get a list of appropriate goodness that consists of newly violated constraints. Add them to the current list. Then in phase 2, do the projection step, project the current iterate onto the boundary of the hyperplanes in the list of violated constraints. Okay, so here we are down in the project, I should say, here we are down in the project step, and we do a Bregman projection. You know, these variables are measuring the distance of the point X from the violated hyperplane. In general, there isn't necessarily a closed form solution for this Bregman projection, but but there are for specific objective functions F. And we're going to compute the necessary update, the necessary correction. We add it to the value of the dual variable. And then in the forget step, we go and we look in the list of violated constraints. If no constraint, if the particular constraint HI has not been updated, i.e. ZI is 0, then we eject it from the list. We forget it. Okay, so we get a list of constraints. We project our current solution onto the boundaries of these hyperplanes that define the constraints. And then we say, who didn't get updated? Kick them out of the list. And we iterate. Okay, so the secret, what makes this work is having an efficient separation oracle. Okay, this is an efficient algorithm that will tell you, whether or not your query point is in the feasible space. And if it isn't, it returns a list of half spaces or violated constraints. And I need to go through carefully what that oracle guarantees. Okay, so why do you need the separation oracle? Well, the problem is the constraints may be numerous. there may be exponentially many of them. Imagine lots and lots of, imagine a convex set with lots and lots of corners in it. Writing down all of these constraints may be computationally infeasible. And so you can really only access them via an algorithm that says, hey, this point is outside this set, or no, this point is inside the set. And you need an algorithm that can do that quickly. So we need a separation oracle. Let's say this is a deterministic version. We also have a random version for a family of half spaces H. If there is some positive non-decreasing continuous function such that the oracle satisfies, yes, the query point is feasible, or it returns a list of these half spaces such that the maximum distance between X and the constraint in the constraints in the list is greater than or equal to this non-decreasing function of the distance from X to the feasible set. Okay, now, what does that mean in words? What it means is that this separation oracle doesn't have to return the entire list of violated constraints, right? Because that might be some fraction, some constant fraction of this exponentially many of them. So it doesn't have to return the entire list. There could be some convex set that the query point X isn't in, but that set also isn't necessarily in the list. What we can guarantee is that the maximum distance from X to the list of constraints is at least some non-decreasing function of X from the feasible set. Okay, so it's like the opposite of no, I was gonna say, you're guaranteed that your list is pretty good. It's not necessarily all of the violated constraints, but it's sort of those that are far away enough. Okay, and you have to be able to demonstrate that you've got a polynomial time algorithm that realizes this property. And in fact, we do, and it is based on an all pairs shortest path calculation. So here is the oracle for finding metric violations. What you do is first you run an all pairs shortest path algorithm, and you compute, what the weights of all the shortest paths is between, pairs of nodes. And then you go and check, is my weight between point I and J, is that greater than the shortest path between I and J? If so, then add that to my list of violated constraints, add that edge to the violated constraint. Okay, so the proposition is that this is an oracle with property 1, i.e. it satisfies this condition that we said in the first page, and this is the non-decreasing function phi, and we claim that it runs in polynomial time. Okay, so every math talk should have at most one proof that that most people can understand. So hopefully this does it. If it doesn't work for you, don't worry, because the all pairs shortest path algorithm comes up again. It gets used again to prove something else, so you have a second shot at it. Okay, so let's prove this proposition. Okay, so the first thing that we need to show is that this oracle actually separates the polytope from any query point. And the first thing we're going to observe is that if I run, say, Dijkstra's all pair shortest path algorithm, it runs in time n squared log n, blah, 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 accordingly. Okay, check. Okay, and now if the shortest path between U and V is not the edge between U and V, then you found a violated constraint. If the shortest paths are all the edges connecting adjacent pairs, then you don't have any violated constraints, and the query point is in the metric polytope. Great. The oracle separates things, and it does so in polynomial time. But let's make sure that it returns a list with the appropriate property. Okay, This is not hard, but takes a little bit of time. So let's let X be my query point. Let's let this hyperplane defined by some cycle C and some edge E be H. And I'm going to define the deficit of this constraint to be the weight of edge E minus the sum of all the other edges in the cycle C. Okay, and if the deficit is positive, then X violates this constraint. So we found a problem. You know, the length of this edge is greater than the sum of these other edges. And the distance between the query point and the hyperplane, the distance squared, is the deficit squared divided by the length of the cycle. You can think about doing this calculation by adding and subtracting the deficit divided by the length of the cycle to each edge weight in the cycle. Okay. Now I'm going to let X APSP be the all pair shortest path metric that I've derived from X. You know, I'm going to take X, I'm going to run Dijkstra's algorithm and find out what the distances would be for all the shortest paths. And I'm going to let L be the list of violated constraints returned by my oracle. And I find out, and I compute that the squared distance between X and this all pair shortest path metric is simply the sum of the squares of all the deficits, cycle deficits in the list. Kind of makes sense if you think about this. And now let's let H of C tilde E tilde be the hyperplane that has maximum deficit in the list L. And I'm going to determine that the distance between X and this special hyperplane squared is, well, it's the deficit squared divided by the length of the cycle. And that's greater than this value is what has been maximized in the list. So it's greater than the average over the list. What do you know? The average over the list size is nothing other than the distance between X and the all pair shortest path metric. Now, the length of any cycle is no more than N. There are N vertices. The list is no more than the number of edges in the graph, which is no more than N squared. So I get an appropriate denominator of N cubed. The distance between X and the all pair shortest path metric is greater than or equal to the distance between X and any point in the metric polytope, because the all pair shortest path metric is in the metric polytope. And this is the distance between X and our feasible set C divided by N squared. And now we put together our string of inequalities, and voila, the maximum distance between the query point and any hyperplane in the list is at most the distance between X and the feasible set squared divided by N cubed. Now all you have to do is take the square root of both sides and you're done. I hope you all are convinced. And I hope you're convinced of the power and simplicity of all pair shortest path calculations. Okay. Should you not be convinced by that, let me go on with the detailing at a slightly higher level the rest of the algorithm and hopefully impress you with some of the experiments that we were able to do. I won't go over all of them, I'll just do some of them. Okay, so, you know, just for completeness, we have a definition here of what a Bregman projection is onto a convex set with respect to a distance function that's defined in terms of the objective function f. So there it is. We have theoretical analysis of this algorithm. It converges to the optimal solution. If the objective function is nice, then we can actually get the convergence rate. And we can also guarantee that inactive constraints remain so for the once they become inactive, they remain inactive. So this is also nice to know. I'm not going to go over all of the experiments for the sake of time. I just want to highlight one particular one that we did because it was so impressive. This was the weighted correlation clustering example. First, we did them on dense graphs because we actually had something we could compare against. So Velt and Gleich and someone else came up with fantastic optimization code that would solve the weighted correlation clustering problem almost, that problem size is almost three times bigger than what you could do with a standard solver. In order to do so, they adjusted the problem slightly to a different kind of LP with an optimality factor in here. We compared against their algorithm, just a sort of sanity check. We're better on these aspects, we're slightly worse in this one, et cetera. But what was really impressive was when we went and looked at the sparse graphs. And at least I would argue that sparse graphs are more realistic for sort of network data sets. And we were able to do sizes that were just utterly unimaginable by sort of anybody else. So these are graphs with 82,000 nodes and 130,000 nodes. The number of constraints that you get for these kinds of graphs are things like of the size 10 to the 14th and 10 to the 15th. And our code actually converged and produced answers. I can't calculate for you how many days that is. 40. This is almost 48, that's 2 days. I guess this is almost 6 days, less than 6, a while, five days. But let me put it to you this way, nobody else could touch anything this size. So it was actually quite impressive that we could do it. And sort of what's really disturbing is that the number of active constraints is like 400,000 out of 10 to the 14th. Which means that, this oracle is very useful. And this notion of returning a pretty good list of active constraints and then removing ones that have become inactive is very powerful. So David Gleich was gracious enough to interview me and Rishi in this sort of hour-long video. He really wanted to know how we managed to pull this off. He wanted to know, was this just some better engineering, or did you actually have some, innovative insight into the structure of the problem that you used? Like, he really wanted to know. So this was a fantastic thing that he did. He recorded the Zoom thing, and he walked us through the paper, and then he walked us through the code, and he did some editing, and he posted it on YouTube. And it was a fantastic thing to do. Like, this is how you should, conduct life in a pandemic, how you should conduct research in the pandemic. And we were able to say to him, most of the innovative work was in the mathematical structure of the algorithm, and then Rishi engineered the heck out of the code. But really, it would not have been possible without sort of understanding the structure better. Okay, so I'm very grateful to David for doing this. It was cool. Okay, so I've left out like a whole bunch of the experiments and the problems that we were able to tackle with this algorithm. There are a number of them in this great big long paper that we have. We extended this algorithm to general convex constraints, not simply metric ones or linear inequality constraints. And we applied them to, weighted correlation clustering, metric nearness, information theoretic metric learning. We have actually a whole separate paper on sparse optimal transport. We looked at L2 SVMs, and it's a very powerful machine. And it's quite exciting, all the things that we can do. What's sort of more exciting is like how it got us to think about problems. Okay, and now I realize that I have about 10 minutes to tell you about the second problem. The good news is that I can do this one. I can skip lots of slides here. And in fact, actually the story that I want to tell you here is that this is the problem that I started thinking about first 3 or 4 years ago. And I went and I looked at the old metric nearness papers of Brickell and Trop, and I said, why didn't anybody replace the LP norm with an L0 norm? That seems like an obvious thing to do. So I'm going to tell you the problem, and I'm going to tell you the surprising answer. I will skip all the details, and I will tell you a bunch of the applications based on these ideas. And I'm going to tell you that it was this problem that got us started thinking about project and forget. Okay, so again, to set the stage for this problem, here are my various definitions and how you should think of this problem. So I have a matrix D of pairwise distances. It is symmetric. The entries along the diagonal are 0, and it satisfies a metric if it's non-negative, real valued. The entries along the diagonal are 0, and triples satisfy the triangle inequality. And thinking of this as a matrix is kind of annoying. So I'm going to stretch out this matrix into a vector form, and I'm going to rewrite, satisfies all these triangle inequalities as a system of inequalities. A matrix M times the vectorized form of D should be entry-wise greater than or equal to 0. Each row of M is going to correspond to a triangle, I, J, K, and it should be like this: all zeros, 2 ones, and 1 negative 1. Okay. And now here's the metric repair statement formally. Given a corrupted metric, D prime, i.e. some triangle inequality is broken, find a perturbation P that repairs or corrects the metric D prime. In other words, if I take this triangle inequality matrix M times D prime plus P, we have entry-wise everything is greater than or equal to 0. Okay. Here, D prime is the corruption of a metric, and P is the repair. Okay, now you might ask, the metric nearness question, which I hope you all recognize was one of my examples from metric constrained problems. You could ask, give me the repair that is smallest in LP norm, i.e. give me the point D that is closest in some LP norm to D prime that lives in the metric polytope. Okay, and here this P is between 1 and infinity. You could make it 1 or 2. Those are usually the most interesting things, the most interesting norms. You could also say, look, the cone, or the metric polytope, that's too general. What if I project onto the cone of Euclidean distance matrices, which would be otherwise known as multidimensional scaling and has been done and used since, 1960 something. So you could try and solve this problem. Give me the closest metric that is a Euclidean distance metric, closest in some Frobenius norm. This is kind of a cute side note. There's a randomized algorithm for matrices, points in R3 that Bonnie Berger came up with in 1999, and you can kind of view that as a randomized metric nearness algorithm. It's kind of cute. You could also say, look, rigidity theory is a way of talking about distances and sort of distorting polygons. Which goes back a long time. It's always good to say your problem originated with Cauchy. The problem with all of these approaches is that they perturb most of the distances. And in fact, actually, they correct or they change a bunch of them. And I don't like that. I want to assume that most of the distances are actually correct, not only a few of them are corrupted. And in particular, I would like to know what is the perturbation that has the fewest number of changes that corrects my input. In other words, what is the closest point to the metric polytope in L0 norm to my input? What is the sparsest repair that I have to make to my matrix to ensure that it lives in the metric polytope? This seems like a completely natural question, especially if you spent 15 years doing like compressed sensing. Why didn't anybody think of this problem? Unfortunately, it is a non-convex problem. And if you are tempted to relax this objective function to be L1, which is like what everybody would do in compressed sensing, it turns out it doesn't work, which is astonishing because you would think from everything you've been told about compressed sensing that this is the right thing to do. And in fact, it's not the right thing to do. It does not give the sparsest solutions in general, and it actually doesn't give very good solutions. So there's a lot more going on than you might think, and you have to dig deeper into this problem to understand what's going on. You know, you really have to think about the combinatorial nature of the problem. And you have to step back and say, you know, what if I asked sort of the stupid question? Could I even efficiently detect whether or not my input matrix D prime is a metric? Could I find broken triangles quickly? Could I answer yes or no quickly? Whether or not my point is in the metric polytope quickly, like faster than this n cubed business? And the answer is probably not. So there's a lovely theorem by Williams and Williams that goes back now to 2010, and it says, look, all these problems are all equivalent. They either all have truly subcubic algorithms or none of them do. Okay, here is the second one in this list, checking whether or not a given matrix defines a metric. That's our problem. So whatever convex relaxation we come up with, we're stuck with all these constraints. Perhaps we should not do all these convex relaxations. Perhaps we should go look at this first problem in the list. Oh, this is our friend, the all pair shortest path problem, which came up in our previous set of problems. So whatever we do, we probably can't do better than cubic time. Okay, but perhaps we can tackle sparsity, which we can't do with convex relaxation. All right, so I'm going to give up on time and I'm going to go for sparsity. And it is at this point that we should remember that I said you need to dig deeper into the problem and understand more of its structure. Okay, so I'm given a triangle and it's broken, and I have bowed out various parts of this triangle to get you to think, oh yeah, there's something wrong with this one. So here 7 is greater than 3. Okay, this triangle is distorted. So there are a couple different ways I could fix this, right? Or a couple different ways I could repair it. Sort of the obvious one is I could make 7 smaller. I could decrease it, make it 3, and then my triangle is good. Okay. I could also increase the 1 to 5. Here I have bowed in the 1 to get you to think, oh yeah, this is the one that needs adjusting. And I increase it to 5, and then my triangle is good. So in the first case, I have positive perturbations. And in the second case, I have negative perturbations. And I have changed 2 different legs of the triangle. And notice, you know, they're not the same. even though they're both sparse. So I get two different sparse solutions. Granted, it's a triangle. You only have 3 legs you can change, but use this as a cartoon. In other words, decreasing our triangle, decreasing our distances is actually quite a bit different from increasing the corrupted distances. And then, of course, the general problem, I can increase and decrease the various lengths. This is also quite different from these. So actually, as it turns out, this version of the problem is simple and straightforward to handle. And these two problems are NP hard in not good ways. Okay, so in fact, actually, if you were to just try and do convex optimization here, you wouldn't see this distinction. You wouldn't see this, difference in structure of the problems. And you wouldn't see actually that there's a beautiful, simple algorithm for decrease only metric repair. It is the all pair shortest path. It is to run Floyd Warshall. When I was doing this work with Lalit, let me explain. Lalit was an undergraduate major at Waterloo, so he had to do both math and computer science. He and I were banging our heads against the wall on this problem for a while. And one day he came in and he said, "Oh my God, Anna, this is an undergraduate algorithms exercise." I had this. So, oh, okay, this is fantastic. It turns out that the Floyd-Warshall algorithm will give you the sparsest solution for decrease-only metric repair, and it runs in time n³ in general. And here is the algorithm. It says, look, if you have a triangle that's broken, if this leg of the triangle is greater than the sum of these 2 legs, then you should decrease this one and you should set it equal to the sum. That's it. That's the repair. Okay. And now you should think, why is the increase only case so hard? Because if you have a broken triangle, you have 2 legs to choose from to increase. Which one you choose at this particular stage in the algorithm may have a horrendous impact on future iterations of the algorithm. And you can't predict that, which is why you get this hardness result, which is beautiful. You can see it right here. I have this inequality. If all I can do is decrease something, then clearly this is the right thing to choose and I should decrease it. And then if all I can do is increase things, if I'm faced with this inequality, I have to make a choice, this one or this one. And it's really not clear which one you should do for later calculations. And that's the intuition behind the hardness result. That's not the proof, but that's the intuition. Okay, so I said I would make this quick. Hopefully you believe this all pair shortest path. Here is the guarantee that the all pair shortest path solution is the sparsest possible decrease only metric repair solution. And in fact, actually it is the right solution to the closest point in the metric polytope for any LP norm. And what's kind of funny is that Brickell et al. Kind of knew this, but not quite. In their original paper. And so I always like to put in their result too, because they were really close. It's just they weren't asking the same question. They weren't asking about the sparse repair. Okay, so I'm just gonna say, once we did this paper, we looked at a number of different generalizations and extensions of this problem. We said, let's do this for general graphs, not just for the complete graph. And hopefully you can believe me that like this is a bowed out leg of this cycle. So it's a broken cycle and this leg here is too small. It should be increased to make this cycle appropriate. And hopefully this sounds like it might be possible to repair the edge weights that one derives from computing the, say, 30 nearest neighbor graph for points that ostensibly lie on a manifold. And hopefully that gives you an idea that you might actually be able to correct the problem that we had with the Swiss roll originally, and give you some idea of not being able to impute missing data necessarily, but being able to correct distances that are calculated from corrupted or missing data points. So these were the two extensions that we did following that work. And, we just, for the sake of time, I'm just going to tell you, we have a bunch of theoretical results. They look like algorithm results, complexity theory results for the graph metric repair. If you're allowed to increase the distances even just by a single number, the problem becomes NP complete. So it's not a good problem. We can show there's a fixed parameter tractable algorithm. If you assume that the graph is xi chordal, for some constant xi, then you can get an algorithm that runs in time that depends on the size of the optimal solution here, and treats xi as a constant. So it's not too bad. It's not great, but it's not too bad. And then, we've applied this to a bunch of manifold repair algorithms, and we've looked at how deleterious corruptions and distortions are for multidimensional scaling, sort of the underlying algorithm for isomap and all of these dimension reduction problems. And so I think that this is a rich, fruitful area of research. It's kept me busy, and my students and my postdocs and my collaborators for several years. And I think we're just at the beginning. So thank you. And I'll take questions.
Sorry. So anyone has questions? So please go ahead.
I have a question. So at the beginning you gave the example of the Swiss roll, and you mentioned it again at the end, but then what was the resolution? Did you run through that corrupted data with your?
Yes. Yes. So I have pictures. They're not in this talk. That's a whole nother talk. Yes, I'm not going to be able to find them fast enough. but yes, well, we actually did this really cool experiment. So people have used this manifold embedding stuff to do classification. And there's a famous digits, it's by now very old, digits data set. It's like handwritten digits that the US Postal Service used to train their OCR machines for sorting your mail. Anyway, we took these digits and we knocked out some percentage, a varying percentage of pixel values, and then used those corrupted images to do dimension reduction and learn a classifier on the reduced things. And we discovered that our algorithms can clean up the data up to about 60% removal of the pixel values. And then about 70–80% everything collapses. But the really embarrassing thing about this work is I was giving this presentation at Microsoft, and somebody in the back of the room who wears glasses took off his glasses, and he says, if you squint, you can actually make out what the digits are in the corrupted data. So actually what this points out is that we should really compare our methods with simple data imputation methods like averaging. Anyway, as somebody who wears glasses and often squints at the back of the room, I thought this was hilarious.
I have just a basic question to make sure I understood it. In the beginning, when you were talking about the optimization with metric constraints, you talked about there being exponentially many constraints.
Possibly.
Possibly. So if you have the complete graph, I guess I was realizing I was thinking about the complete graph, then is it you just have the triangles and you would just have n cubed. So you're thinking of and so I'm just curious about this because I never thought about this, but for say some arbitrary sparse graph, is it known that there is not some kind of set of smallest cycles or something that could be used in place of triangles that might be smaller than exponential?
Oh, you know what? I don't know. Yeah, okay, that's almost like saying, isn't there some core set of cycles that you could use? And hey, actually, you may not actually be asking this, but many of these FPT proofs use, like a core set. I don't know because that's not how our FPT proof works. So the answer to your question is I don't know. That's not how we were able to get things to work. It's very tempting to think that way. We couldn't make it work.
Okay.
You might ask, is there some core set that would give you an approximation? We do have approximation algorithms. Is it in here? Oh yes, here we go. There are actually several approximation algorithms for sparse graph metric repair, and there are two different kinds. One is parameterized by the length of the longest cycle, and the other one is parameterized by the deficit of the most broken cycle. Anyway.
Thanks for the talk, and I have a question that maybe is a follow-up on Melanie. So this table went by really fast with this very impressive number of 10 to the 15 constraints.
Yeah.
And I'm assuming that number was like the number of potential constraints, or maybe n cubed. You didn't actually examine 10 to the 15 constraints in a week.
No.
Okay.
No.
So what does that mean, number of constraints?
So that means if you count up all of the cycle constraints in a graph of 82,000 nodes, that's how many there are. So a cycle. I'm gonna draw a bad picture. Cycle looks like this, and you want this one to be less than the sum of all these other guys. This one to be less than the sum of all these other guys. You see how you there gets to be a lot.
Do you consider cycles of arbitrary length?
Yes.
Wow. Okay.
Yes.
Up to length 82,000? That would seem closer to n factorial than to 10 to the 15th.
I'm not sure actually what the structure of this graph looks like. So maybe I should say we consider cycles up to the length of the longest one. I don't know. What
I see. So the graph may have very few cycles. I actually
don't know.
Okay, but it has triangles in it.
Yeah.
Lots of triangles that are constraining things. Okay.
Yeah, in fact, actually the FPT result says, hey, if the graph is chordal, then there are some approximation algorithms.
Oh, I see.
So anyway.
Okay, thank you.
Yeah.
All right, so any other questions?
I saw something in the chat, but I have problems with Zoom and
chat. Yes.
Oh, the squint algorithm. Yes.
Sorry, it was not in serious. I was just joking.
Yeah.
it's okay. Yes, I think the Gaussian blur filter should be known as the squinting algorithm.
Any other questions? So, all right, so maybe let's thanks Professor Anna Gilbert for a very interesting talks. Thanks a lot. Thank you.
Thank you.
And then we end today's colloquium here. Thanks.
Okay, great.
Thanks, everybody.